Hi everyone and welcome back to my channel. So in my last PIV tutorial, I was explaining about how you can set up your own PIV setup and how you can install a laser and a camera to understand the flow field. So in the same video, I showed you a video of how a flow over an airfoil would look like. So I've taken two images from the same video. Mind you that these are consecutive images. You should not take any two random images because they won't give you the good result that you would be looking for. So this is an image at instant one. I'm calling it as instant one to show that it's the first photo, and this image is taken just after the image one is taken. So this is called as instant two. So as you can see that there is a vertical shift in these two images, and from this we can qualitatively say that the flow is in y direction, or to be more specific, in the negative y direction. And today we want to see what is the displacement, and furthermore, because we know what the delta t from the camera would be, so we can furthermore calculate what would be the velocity. So the tool that is used to calculate the displacement, it's called as cross correlation. So I'd be using MATLAB to demonstrate how the cross correlation is done. So let's just get started with that. First, I'll explain you what that is. So we want to study these two images. The same image that called instant one, the next image is called instant two. And because they look really messy, so let's simplify the system first. So I just have modeled these two black rectangles. So the black rectangles are just the background and the blue ones are the particles, the seeding particles in our PIV system. So to make life easy, I've just shifted all of these blue particles in the y direction. So you can see that some of the particles at the back or the bottom, they are not included in the picture because in the next frame of your PIV camera, these particles would be out of the field of view of the camera and they won't be included. And I'm not including the particles that could pop up from the top because I just want to explain how cross correlation works. So because this system, it looks quite big, there are a lot of particles, so we don't deal with the whole system. We apply a very simple strategy, divide and rule. So we divide our original image, or you can say the image A or the first image, into some parts, and we call these parts as the windows. And windows is a very frequently used term in PIV. So we divide the image in windows. So we now got four windows in the picture over here, and the next step is to further study these windows separately. So now I want to see where my this small window would sit in the bigger picture over here. And if I could just locate the location of this small window in my next instant, so this red one over here, or the one image on the right, is uh-oh, yeah, just okay. Sorry for the mess up. Yeah, so the image on your right is the instant B, and this small window is from the instant A or instant 1. So I want to know the location of this particular window in image B, and from the center points of the two windows, we can actually get the displacement. It's as easy as that. So rather than dealing with the whole image, we're just cutting down those image in some parts, and rather than studying the displacement of the entire image, we are trying to study what is the displacement of individual window. So we'll do the same thing for the other windows. So once we know what is the displacement of this window, we can separate this particular window, or we can just try to find what is the location of the window in the other image, and that would give me dy. So before I go any further, there is a tool in MATLAB that is called as the norm x core 2, which is normalized 2D cross correlation. The 2 is for 2D. So the job of this command or the tool is to do exactly the same thing that we have just seen. So this is the entire image. So you can consider this as the image B or instant 2, and you can consider this as the part of the instant 1. So you can just imagine that this is the like the smaller window from the entire image. And now using this tool we can locate the location of this smaller window in instant 2, and using norm xcore2 we can actually pinpoint the exact location. And we actually want to do exactly the same. We want to see where this small window would sit in the instant 2 image or image B, and by knowing the exact position we can find the exact value of the displacement and therefore the exact value of the velocity. And that's why we are doing PIV. So to make windows in MATLAB we can simply uh, do this technique. So to get the coordinates of your windows, you can have an arbitrary coordinate xy, and if you're assuming that your windows are square in shape, then you can get the points of other coordinate just by adding the w, that is the width of the window, to the x and y coordinate location. And you'll also know the x and y locations of the or the x and y boundaries that I'd say for each window. So if for this particular window I have my center point or the midpoint as xy, then the left boundary would be located at x minus w over 2, the right boundary would be located at x plus w over 2, and the same would go for y, that the y bottom would be y minus w over 2 and the y at the top would be y plus w over 2. And because if you observe that in norm x core 2 you need a statement of this particular form, that you need a template which would be our window, and you need a further matrix or an image that it needs to search in. So in this example they are trying to search this particular image in this whole image. So they will actually move this small piece of image at every point and try to find where it fits the best. But because we are doing PIV, we are doing an actual experiment, so we do have some idea on where the particles would move. So we are sensible because we do have common sense. So we can actually say that rather than searching for in the entire image, why don't you just search in the neighborhood, because these images are taken at a really short interval of time, so the particles won't really escape into some unknown territory, so better to search just nearby. So small this small square is my original window, and the blue highlighted colored the square is my search zone. So I'll try to correlate this small window of image 1, which I have separated here, and this bigger square of my image 2 or the instant 2, and using the norm x score 2 I'll try to find where the maxima is, or where the window would shift. And once we know where the window shifts we can get the dy. So, and one more thing, so there's a command in MATLAB, it's called imread or image read. So this command is used to read images. So because I have these two images, I only have this data, I just have instant 1 and instant 2 photos, and I want to locate all the dx and dy. So without any further delay, let me just show you the code. So in my first three lines I'm just clearing all the variables in there. I'm clearing the command window, I'm closing all the windows, so this is optional. Furthermore, these two lines, it's just taking in the images. So I'm calling image A to be instant 1, image B to be instant 2. I'm using imread command. So these are just making from the TIFF file. I'm storing those TIFF file as a matrix in image A and image B. And X max, Y max is size of image A, because image A and image B are the same, because they are of the same size, they are from the same camera. So I don't really need to separate them as X max A, X max B. and this is like the overall dimension, or if you have a camera, which it's just the size of the image basically. And here comes the important thing. In here, I'm defining what I want my window size to be. So these images are fairly big. So in this code, I'm using a window size of 64 by 64. So that basically means that if my image is, say, 1024 by 1024 pixels, that is that these are the values of pixel in each direction. So I want my window to be 64 pixel by 64 pixel. I think it would be a good idea if I show you how it looks like. So I've just executed this particular part of the code, and I've got image A and image B. So to show you what image A looks like in MATLAB, so image sc is the command to look for the image. So don't worry about the blue color, it's just the coloring pattern of the MATLAB. So this is how it looks like. So my image is roughly 1024 pixel, or probably 1100, I'm not so sure. And in this direction, it's around 1900 pixel, a bit less than 1900. So I'm using a window size of 64 by 64 pixels. And I'm just saying that, okay, the height is 64, the width, the height and width are both 64. And there is no problem if you want to use some square shaped, rectangular shaped windows, that would be totally fine. And now comes where I want to define windows all over the domain. So I start from, so X grid is the array for the X coordinate of all the windows. So I'll say that the windows start from 200 comma 200 if you read them correct together. So that would be, it starts from 200 comma 200, and it goes up to 864 in X direction, because, and in Y direction it goes up to 1696. And just to show you once again, because in MATLAB this is your X direction and this is your Y direction, because in MATLAB they understand it in terms of rows and columns. So the row becomes the X and the columns become the Y. So the row goes like this and the column goes like this. So there could be a slight confusion if you're not already familiar with this terminology. So just to keep things simple, this is X and this is Y. The Y is the horizontal direction here. So probably my windows would start from somewhere over here, and it would go all the way probably till here. So I'm dividing my images into these sizes, and you can see that there is the width over 2. So it's just the same thing that I explained in the PPT. So because this is like the W over 2s, so that is that. And finally, I'm using my common sense once again for the search zone. So I'm saying that if the image B and the image A, or you can say that the the location of the search zone in image B, it should be plus minus width over 2. So to make things easier, so I'm saying that this thing it would be W over 2, and this thing it would be W over 2, and this thing and that thing on the top and bottom there would be W over 2. So this thing could vary according to what is the order of the velocity field that you're trying to measure and what is the time delay. So you can try to play along with these things and see how they affect your result. And then I'm saying that I'm just initializing the test image A. It's just basically the individual window of an image A. So that's just the window actually, the 64 by 64. I'm just initializing it to be 0. And in image B it would be the bigger one, including the search. So that is 64 plus twice the search zone on both sides. So that includes left plus right. And the same goes for the other direction, the top and bottom. I'm just initializing it to be 0. dpx and dpy are the displacement in x and y direction for every window. I'm saying that to be 0. And just ignore this for a while. It's to get the maximum value of correlation. And the maximum value of correlation would indicate where the window would fit in your image B or your instant 2. So I'm using for loop for every window because we want to investigate every window. And once we get the data for each window, we combine that data and that becomes the whole picture. So for every, so these two loops they are recursive for every window. And for every window, I know these x minimum and x maximum is just the left and right x coordinate, and the y minimum and y maximum are just the top and bottom boundaries. And I can make the image A or the window of the instant one using the maximum and minimum. So I'm just saying that in x direction it would be from x minimum to x maximum, and the same would be in the y direction. And for the instant 2 I would have a bigger size of window, so that would be from x minimum to x displacement maximum, or to be more specific, if this is x minimum, I'm sorry, if this is x minimum, then this boundary would be x minimum minus w over 2, or in this case I'm saying w over 2 to be x displacement maximum so that I could vary it. It's a good idea if you're coding stuff, then better to play in terms of variable than putting actual numbers here. And the same goes for the other direction, that x maximum plus displacement maximum. And the same goes in the y direction, that y boundary at the bottom minus the displacement boundary, and y boundary at the top plus the displacement boundary, then that would give you the image B. So basically this is the image A in the black, and the blue is the test image B that I'm using in the code here. And I'm calculating the correlation using the norm x score 2 between the image A and image B, or the test image A and test image B. And using this particular command, I find where the maxima in that correlation is, and that maxima would correspond to where the image has moved or where the window has moved. And don't worry about this stuff for now, because the norm x score 2 command, it's a little bit tedious, so it it does some stupid stuff to the coordinates, and it moves around the peak. So this is to just get the peak at the right place. So if you're curious, you can study it. And further, after this is done, I'll just get a vector plot. So I'll just run this code. And I hope that the explanation would be clear, but there's a good chance that I may not be very good at explaining this. So just throw up all your doubts, and you might want to just see more on these codes over here. So study a bit about the norm x code 2. It's really a very powerful tool in MATLAB. So this is it. So then you get a plot like this, and if I just zoom in a bit, and then you can see how these vectors, they point in the vertical direction. And then I can play with my window size. Once that is done, I can try to make the windows bigger. So one thing that you'll observe here is that this is the one with the 64 by 64. And if I am making my windows bigger, then it means that I am having lesser windows in my entire image. And that would mean I would have a lesser PIV resolution, as you can see once I get the results. So you get a lesser number of arrows, or you get actually the lesser number of data points from your post processing. And if you, and there's a trick here, and if you're really looking for very high resolution, and the first idea would be to make this window size smaller. And once you make the window size smaller, then that implies that the number of particles in the windows would start to go down. And once that happens, there are some bad things that might happen to cross correlation, as you'll see in a bit. So as you make the window size smaller, you get all sort of uh, these are actually called spurious vectors, and they are just like some stupid stuff that happens because of the lesser number of particles, and sometimes even because of if the delay is smaller or the delay is much larger, or it could be because of a number of factors. So that's a whole thing in itself, like how we can remove these vectors or what kind of pre-processing could be done for the images so that we don't have these vectors. But that thing is to be taken care later. So I hope that you get some idea about how to do a cross correlation. I hope that you understand what is cross correlation and why do we need it, and if we need it, how do we do it, and what after we're doing it, what kind of data can we obtain, and under what circumstances are these useful. So in case if you got any questions, just feel free to ask me anything, please. And if you like my video, please hit the like button and subscribe to my channel. I'll keep posting these kind of videos to help you and your research. Thank you so much. See you in the next video.